And the last speaker in this session is going to be Gabin Maxime Nguegnang from Ames, Cameroon. And he's going to talk about analysis of gradient descent and SGD for learning linear neural networks.
Yeah, thank you. I would like first of all to thank the organizer for the opportunity to share our work to this nice conference. So I'm going to share part of my research in my PhD, which is supervised by RWTH and also Boubacar Ba. RWTH is a researcher in our chair in Aachen. So I'm going to first of all present part of the state of art in order to present to you how our results fit into contributing to these directions. So as we know, deep learning is now like the main agents of modern industrial revolutions. And we can see the evidence and the impact in many areas, like using object detections in medicine and many more areas. I also have the opportunity during my master at Ames to experiment machine learning and neural networks on fuel consumption data, whereby we were able to analyze some data from telecommunication base stations, and we were able to build up a model that could help the company to enhance its economic for about $70,000 in a very short time, and that was like the key the main catalyst of my interest into neural networks model, because we wrote 2 papers where I intended initially to explain how this model works, and it was quite a bit interesting with some decision tree machine learning model, but with neural networks, I then realized that this was a widely open question. So I was then motivated to move forward to understand more, and then I applied to this position in Aachen. And then while exploring the literature, I still realized that even the most simpler model is still not well. I mean, the mathematical principle behind this is still not fully developed. So, and beside the impressive result, we can also observe some cases of failure. I remember listening a talk of one leading expert in AI, Joshua Bengio, who said that everyone who use machine learning system knows that they sometimes make stupid mistake. And with this picture, we can see a machine learning model, a deep learning model that's supposed to ask a car to stop. It's giving the authority to continue with a speed of 45. In this case, this is a failure which could be a grammatic. If you are worker doing something there, and it can be very dramatic. And on top left, okay, in this case, it could be nice, because if you are looking at your Labrador and the model help you to find a KFC box, then you can just enjoy the chicken. Yeah, so but we would like to anticipate in this type of error, and the main thing to do here is really to understand the mathematical principle behind. We aim at analyzing one of the most simple models in order to provide tools that will help to facilitate the more complex model, which is a nonlinear model. So then present our setting. So we have this is a network. We also first address the fully connected neural networks that the previous presenter already introduced. And I want to say that when you process the data, it corresponds to these compositions. And in our case, we use a linear activation function. So in practice, we use a nonlinear activation function, which is actually the composition of a linear map and a nonlinear term here. So when this is linear, the neural network is said to be a linear model. So, but when you process the data at the output layers, we compute the empirical loss, and usually the learning process consists of optimizing this error through a backpropagation, which mainly rely on algorithms like gradient descent and on stochastic gradient descent. So knowing that this is an iterative process, the question is, do we really find a global minimum, because the structure of the cost is really highly non-convex. And we first simplify the model by using linear activation functions. So the corresponding network would be the one that you see in one. Here, this is the factorized matrix and the input data. So on the cost, we observe the cost with two functions, which are actually the same, but only that we move in two different ways. So the Ln is the network of depth n, where we consider a tuple of matrices, which is actually the parameters of the network. Like W1 will be like moving from the first layer to the input layer to the first hidden layer, and so on. And this L1, we realize that both are the same. Like the difference is that with L1, the input is a factorized. Oh, sorry. With L1, the input is a factorized matrices. So here we are on a manifold of a certain rank, which is lower or equal than the minimum size of this dj. And we will see why this is important to observe both later. So, and the learning process, as I said, is to optimize these cost functions. So, and there are a lot of work that has been done in two directions. So the first direction, observe the gradient descent with an infinitesimal step size, which is correspond to gradient flow. So the result by Barr and his collaborator generalized previous result by considering a less assumption. One reasonable assumption that they use is this assumption on the input data, that the data times its transpose should be a full rank. So with that, they were able to prove that gradient flow will be well defined and will stay bounded, and more importantly, it will converge to a critical point. And then they complement this result by also providing for almost all initialization the convergence of gradient flow on a manifold of a fixed rank. This corresponds to a global minimum of L1, which I presented earlier. And this is on the case of 3 or more layers. But on the case of exactly two layers, we know exactly where gradient flow will obtain the global minimizer. We can say that a priori. But with a deeper network, we can't say it a priori. But the result guarantee that you will meet the global minimizer. And the question is, could we get this with a practical step size? Because gradient flow is an infinitesimal step size. So at least what we want to address. With this plot, we can see how similar gradient descent in green is to gradient flow. So this helps to already expect that some property of gradient flow could be transferred to gradient descent. And one major challenge in extending continuous result with those who usually study models, where you have a continuous model that you want to transfer some of its property to a discrete model. Usually the main challenge is that when you discretize your model, you lose some important properties. This was the case also with gradient flow. So this is well-known property with gradient flow is usually called the invariance of the dynamic of gradient descent, which means that this difference of the weight stay constant throughout the learning process. But when you discretize your gradient flow, then you realize that this is no longer possible. And this was one of the core arguments that helped to establish gradient flow result. But as we will see later, we were able to show that although it wouldn't stay constant, but we can measure how far it deviated from being constant. It's also called the exact balancedness with gradient flow. So the other direction directly addresses gradient descent itself. But given that the structure or the cost function is highly non-convex, people usually consider an abstract function where they impose some conditions. Like, for instance, this nice condition, which is mainly used in optimization, that impose the gradient of the cost function to be Lipschitz. And this is the Poyar-Loyer-Zewicz condition that is also well used in optimization to establish results. So with that, we realized that Karimi and his collaborator established this result with these step size. We could obtain the convergence of gradient descent for minimizing a non-convex function. So but the main challenge here is that when you have an explicit loss, as what we saw before with ln, the factorized matrix of the network do not allow you to really, this condition cannot be satisfied, and it makes that difficult to directly apply such a result with a neural network model. And so later on, the Art and his collaborator tried to address a typical neural network, but then by considering what we usually call, they usually call in the literature, whitening data. By whitening data, they mean that if you transpose the data, if you multiply the data times its transpose, and this is this M is your, the number of data points in your data set. So if this is equal to identity, you say your data is whitening. So with that condition, they observed that gradient descent could optimize efficiently a non-convex function with the help of a regularizer. And we also have some nice results where they impose with the subgradient descent, they impose the iterate to be bounded in order to establish convergence. But we know that as an iterative process, the iterate can always escape to infinity, so we really need to have a careful analysis to ensure the boundedness. So one of the first results that concretely addressed a linear neural networks was developed by Butler and his collaborator. So they were able to observe that if we initialize the network with a value that is very close to the global minimum, or we consider that the minimum is attained when all layers are positive definite, then gradient descent will converge. But this was for a very particular subclass of neural networks, the residual linear neural networks. So it's a particular network where the dimension of the input layer and the dimension of all the intermediate layers together with the dimension of the output layers are equal. So that later on, Aurora and his collaborator generalized, they extend the result of Bartlett by considering further, providing a more general setting where they could admit the intermediate layer dimension to be greater than the output and the input layer dimension. So but the only limitation of this result is that this will also exclude some important models such as autoencoder, which require that the intermediate layer dimension should be lower than the input and the output layer dimensions. So but Aurora, in order to develop their result, they add this further condition at initialization that this represents the factorized matrix of the network. So this is like the product of the last layer up to the first layer. And this phi is a target matrix that involves the output data and the input data. So they said your condition W, like the factorized matrix, is said to be deficient merging C if this inequality holds. And they also measure how far the weight of the matrix is deviated from being exactly balanced. So they call it a balance, delta balance. So when they say the weight of a network delta balance, they mean this inequality is whole. So with this initialization, they were also able with whitening data to prove that gradient descent will converge to a global minimizer. So as I said, this condition is very strong as a condition, and this would exclude some important model like autoencoder. So we see later on how our result complement this result. And another one use linear regression. This is a result of Cohen and this collaborator whereby they consider the zero initialization to also, this is very similar to our result in the sense that they observe, they're trying to extend the result of gradient flow to gradient descent, but just with a linear residual. I mean, they consider a one dimension, whereby the difference with our own result is that we use a multi dimension. So we have a data set which is a matrix of a certain number of data points, but in this case, you only have a specific a data point. So far, the state of art result has some gap with what happened in practice, in the sense that the condition that it's used to develop the mathematical principle cannot be observed with practical model, like this Lipschitz gradient condition, and there are some limitations on the initializations, and also they always assume the boundedness of the iterate, and there's a lack of a more general result of gradient flow to gradient descent. And most of the result of stochastic gradient descent, whereby they mention the convergence of stochastic gradient descent, it's only indicate that the second moment of the gradient converge to zero. So it doesn't really say that we are going through a critical point. So in order to fill this gap and connect more the theory to practice, we came up with this lemma that provides a bound of the factorized matrix. So I just want to remind you that this W is the factorized matrix of the network. So with this lemma, we say if we use the same condition as bar and its collaborator, then we can bound the factorized matrix during the training process with a constant that depends on the input data and the output data with the initial value of the functional. So under this condition and this other condition, that's this is the iterate of the loss throughout the learning process. So we could bound it with the initial value of the loss, because that will be decreasing. So with this, we also introduce a similar concept like Aurora, with the difference that we use a spectral norm and not the Frobenius norm. So we also call it the balanced constant. It means that if you have a tuple of n matrices, there will be balanced constant delta if they satisfy this relation in 4. So with this balanced constant, we are able to provide this proposition that guarantees that if a tuple of matrices satisfy this delta balance condition, then you could bound each component of this n tuples of matrices. And this is a very nice information, given that the previous lemma guaranteed that we could bound the factorized matrix. So the bound of each component involve the spectral norm of the factorized matrix. So if you substitute the bound of this here, then you can also obtain the bound of each factorized matrix. But the question now is, could we have it with gradient descent? Because the goal is to ensure the iterate of gradient descent is first bounded in order to expect convergence. So we did that with this proposition, where we still consider the same condition on the input data, and now we ask to, I will present the condition on the step size in the upcoming slide. So here you initialize the weight with the balanced constant delta, which means that at initialization this inequality holds. Then what this proposition is telling us is that if you do so at initialization, throughout the training process, your weight matrices will remain approximately balanced. And more importantly, the iterate of gradient descent will stay bounded. So one important result in the study of iterate algorithm is the one developed by Abzis and collaborator that mainly uses Lyazewicz's gradient inequalities. So they came up with this condition usually called the strong descent condition. An iterate algorithm satisfies the strong descent condition if 6 and 7 holds. So 6 only ensure that the angle condition is satisfied. Like you really always point in a way that the angle will favorize you're moving toward the global minimum. So, and the second one, just ensure that you avoid stagnation. So, ABSIS were able to show that if this condition is satisfied, while analyzing or minimizing a analytical function, you have two scenarios. So either your algorithm will escape to infinity or the limit will exist. So given that in this proposition, you already guarantee that the iterate will stay bounded. So applying the theorem of ABSIS already provide the limit of gradient descent. So then we use that to establish our first main result, where we show that gradient descent will converge to the critical point of Ln, and with this condition, the step size. And one nice feature of this step size is that it does not decrease exponentially as it is the case with the state of R result. So when we observe the geometry of a neural network course, we ask ourselves, okay, we converge to a critical point, but which type of critical point? Is it a global minimum or a saddle point or simply a local minimum? But with the result of Kawaguchi, we already know that for a linear neural networks, any local minimum is ultimately the global minimum. We could see from this result of Lee and his collaborator that for almost all initialization, gradient descent escapes strict saddle point. And the intuition behind this result is the following. In dynamic system, if you have an algorithm that is defined by J, and that the Jacobian of that at the critical point has like the minimum eigenvalue is strictly greater than 1, then that point will be a repelling point, so that it will be repulsion. Any trajectory coming there will be rejected. So when you observe gradient descent that way, the Jacobian is given by an identity matrix minus the step size times the Aachen. So at the strict saddle point, the minimum, the eigenvalue of the Aachen has at least one negative eigenvalue. So if you substitute that negative eigenvalue here, then this point, this matrix will also have an eigenvalue that will be strictly greater than 1, which already give an intuition that a strict saddle point will be avoided by the gradient descent. So we apply that by using this result of bar, which is a key tools that connect the critical point of Ln and the critical point of L1. It basically tells us that if you have a critical point of Ln, you can use it to define a factorized matrix that will be a critical point of L1. And one more important information here is that if a critical point of Ln is not a global minimizer of L1, then that critical point will be a strict saddle point of Ln. But we know gradient descent will escape such a point. So with that, we extend the result of bar and provide a convergence of gradient descent for almost all initialization, this time with constant step size and a decreasing step size. So for stochastic gradient descent, we need some important tools of approximate stochastic method, which is given by Benaim, that also can connect, like we interpolate the discrete algorithm to define a continuum process. And one important information here is that it says if you have a continuum process that satisfies this limit condition, then that process would be an asymptotic trajectory of a certain flow. So the flow is a diffeomorphism that satisfies these two conditions. So the important information here is the following. If you fix T, then this means the interpolated process would be a shadow of a gradient flow. So knowing that gradient flow converges to a global minimizer, then this also already give an intuition that we could also extend the result of gradient gradient descent to a stochastic gradient descent. Yeah, this is what we are about to finalize. It's an ongoing work where we apply some classical result from quasi-martingale to establish the boundedness almost surely of stochastic gradient descent and to extend our result from gradient descent to stochastic gradient descent, but almost surely. So with this plot, we just illustrate our result. At the top left, we have the progress of the loss with the step size that exactly meet this bound. In this bound, this B is actually the bound of the Aachen. So we did that for the network of depth 2, depth 3, and depth 5. And we observed that higher value of the step size provides faster convergence. Here we just reduce the step size and observe that it needs more iteration to observe convergence. So down here we illustrate the fact that when we evaluated our condition, we could still observe convergence, but with this plot on the bottom right, we show that violating our condition may lead to the complete loss of convergence. So, which means that it's a good condition, but it's not very tight yet. But it's good to initialize very close to our condition, or to respect that condition in order to avoid losing convergence. This is the same simulation, but with decreasing step size. So I would like to just give this as a takeaway message that the state of art result has some gap that we contribute in complementing this result by establishing, providing a more careful analysis to ensure the boundedness of the iterate of gradient descent, and to provide a convergence of gradient descent for almost all initialization. And we are now working to extend this result from gradient descent to stochastic gradient descent. Thank you.
Thank you very much, Gabin. Are there questions?
Thank you, sir, for the presentation, although I came late. My question is concerning slide 16. You talk about, you're talking about the unstable point. Yeah. I don't know, but from what I understood, if the eigenvalues are positive, meaning we have the equilibrium point is unstable. But how are you talking about greater than 1? So what happens if the eigenvalue is 1?
Yeah, that will be a saddle point. But I was talking about the characterization of a strict saddle point. I mean, in dynamic system, this will correspond to an equilibrium. And this, if the eigenvalue is 1, it means that that equilibrium will be an unstable fixed point. And if you want to translate in our own context, it will be a saddle point. But we are sure that if the eigenvalue is strictly greater than 1, then it will be a repelling point, so that any trajectory going there will be the fixed point will repel it. So with gradient descent, what we are saying is that given that that point will be a repelling point, so any trajectory of gradient descent will not be able to go there. That's what we're saying. Gradient descent will escape that point.
Okay.
So but there are other saddle points which are not strict saddle points. So but we are not talking about those points. That the result show that if a critical point is not a global minimum, as I was saying, it will correspond to a strict saddle point. But since we are avoiding it, we will not have an issue to stay there.
Okay, thank you.
You're welcome.
Anyone else? Maybe I could ask a quick question. So somehow my impression is there is a lot of work in this area. You showed many theorems. If you could say shortly, you know, like what is the main novelty, you would say? What is the main selling point in your work that distinguishes it from other papers?
Yes. Thank you. It's a very nice questions. So one of the main things that, first of all, our result directly address a concrete neural network cause. So there are a lot of gradient descent papers that only assume we have a non-convex function and they impose some conditions. That's the first features of our results that we first address a concrete neural networks, and also we provide a more flexible initialization method. So the result works for almost all initializations. But if you see, they are very specific. There are many results with a very specific initialization, like zero initialization. And the other thing is that we do not, we have a more flexible condition on the way we initialize. For instance, I presented this. Yeah, this condition, for instance, so our result will involve more model, because this condition, for instance, will exclude some important model like autoencoder. So this how our result complement those previous results with this. So and the only assumption that we are doing is a reasonable assumption, because this, given that the data are collected randomly, so this condition can always be observed with a high probabilities. And there are a lot of the other conditions in the state of R, most of them are not really directly applicable when you consider a very explicit model.
Sorry again. Let's say like you are my brother. Like after doing this in Germany, you come home. So if you want to explain this thing to me, like I do not go to school, what will be my take-home message concerning your work?
Nice question. Yeah, like if I want to explain this in another language, I would just maybe use application to make it easier. Like what I said earlier with the first slide, that we have some data. The data usually concern, when we have a problem in companies, we have data that could help us to solve those problems. And there's model that can help us to extract information from this data to solve those problems. But the thing is, given that we can always solve it, and at times we can fail while doing that. So what this work is doing is trying to help us on how we can anticipate in avoiding making such a mistake, like to avoid all those mathematical concepts. In simple word, I would just say something that can help us to anticipate in error that model makes, or to understand more those models.
Okay, thank you again, Gabin.
Oh, okay.
Thank you to